Hi, and welcome to the WellnessFX video training module where we talk about the metabolic panel that specifically looks at the three markers: cortisol, insulin, and insulin-like growth factor 1. And in this video, we'll basically just talk about what each of these hormones are, where they're produced and why, and a little bit about what they do in the body, including what you might see if they're excessively high or low. So let's go ahead and start. We'll just start with insulin. Insulin is made in the beta cells of the pancreas. The beta cells of the pancreas respond to glucose levels in the blood. The higher the amount of glucose, the more insulin they will release and then keep synthesizing to help try to get glucose out of the bloodstream and into the cells and tissues of the body. Now it does so basically via this process. Glucose by itself cannot get past the phospholipid membrane of the cells of our body. It needs some transporter, some channel, in order to allow glucose to come in. Now, the most abundant cell type in terms of our overall body mass is going to be adipose tissue and skeletal muscle tissue. And in those particular tissues, we have a glucose transporter called the GLUT or GLUT4 transporter. It just stands for glucose transporter. Now what that is, in skeletal muscle and adipose tissue, this GLUT4 vesicle, if you will, are channels or tubes that, when embedded in the cell membrane, will allow glucose to come in. When insulin levels are low, those GLUT4 vesicles remain inside of the cell. There's no need to take glucose out of the blood and bring it into the cell if glucose levels are normal or low in the first place. So insulin then is signaling to the cell that there's a lot of glucose circulating outside of the cell, and we would really like to bring that in so that glucose, as you know, if it stays in the bloodstream, can interact with proteins through a process called glycation or glycosylation and make products called advanced glycated end products, which are associated with a number of different chronic and degenerative diseases as well as aging. So we want to get glucose, if it's elevated in the bloodstream, out of the bloodstream and into the cells. There are so many skeletal muscle cells and so many adipocytes that those are great places to take it. And under the influence of insulin, so the beta cells of the pancreas have GLUT2 vesicles, incidentally. They sense the amount of glucose in the body or the bloodstream. They produce insulin because of that. Insulin binds onto what's called an insulin receptor, and through a variety of intracellular interactions, phosphorylations, and a variety of different things, this GLUT4 vesicle brings its transporter tubes, if you will, into the cell membrane and allows glucose to come in. And again, this is going to be primarily in adipose tissue or fat, as well as skeletal muscle. Now, I do need to say a quick comment about this. Is this GLUT4 vesicle what's called translocation, which means it goes from the cytosol within the cell and then embeds itself into the phospholipid membrane, allowing glucose to come in, requires insulin to do so, but not exclusively. In skeletal muscles, it's been shown that skeletal muscle contraction can actually do this translocation without insulin. So anybody that has any level of glucose dysregulation, insulin resistance, high levels of hemoglobin A1C or glucose, as we talked about in a previous video, a cholesterol to triglyceride ratio that's less than 2:1, anything that indicates there's blood sugar dysregulation, relatively high glucose, they must be doing some kind of considerable exercise. And I mean considerable, that walking probably isn't going to cut it, because you're really not contracting your skeletal muscles to the degree that you need to in order to translocate the GLUT4 vesicle to the membrane to allow glucose to come in. So insulin will stimulate this translocation process as well as skeletal muscle contraction. So if anybody has blood sugar handling issues, vigorous, strong exercise will likely help this process quite a bit. So insulin is one of the markers on this particular panel. Let's just talk about what's some different things that you can see. Now, insulin by itself is a good marker, but really makes more sense, again, if you can evaluate it along with all the other blood chemistry markers, specifically things like fasting glucose, hemoglobin A1C, as well as the cholesterol triglyceride ratio, which all look at blood sugar dysregulation. But what you really want to see is if somebody has high glucose, the question is why? So here's really what is the progression down towards diabetes, starting very early with, let's say, for example, reactive hypoglycemia. So here's what you would see in somebody with reactive hypoglycemia. You would see, for example, low glucose, or maybe let's just say low or low normal glucose, Hemoglobin A1C would be fairly good, but high insulin. So if an individual runs this panel, insulin is high, and you're able to look at other panels they've run, which look at hemoglobin A1C, looks at fasting glucose. If those look normal, but insulin is high, what you're looking at is normal levels of glucose getting into the cells, but only because insulin is so high. This is really considered to be the first step down the pathway or the journey to eventually diabetes. Now, it may not be for a couple decades, but if somebody has hypoglycemia or hypoglycemic tendencies, low glucose, normal A1C, but they have high insulin, what you're looking at over time is that all that insulin may cause a downregulation of the insulin receptors, making glucose not come across into the cell. And whereas they had low glucose before and high insulin, in a few months, 6 months, 9 months, they may have normal glucose now and still high insulin. So that's one of the first steps down towards insulin resistance and diabetes. Next, let's take another example. Let's say somebody has, similarly, normal glucose and maybe a hemoglobin A1C of around 5.5, maybe 5.6, and insulin is high. Again, what you're looking at is somebody that has glucose dysregulation. The glucose is actually maybe normal, A1C might be a little bit high, the insulin is high, and what you're likely looking at is that the pancreas is responding to the high levels of glucose and producing more insulin than it would normally, because glucose is not getting into the cells because of insulin resistance. The cells, the receptors, are really not working appropriately. Then, again, going even further down this pathway, you may see an individual that has high glucose and high insulin. Now, this is very problematic because physiologically that doesn't make sense. If insulin is high and it's working well, you would expect to see either low or normal glucose levels. And really, insulin shouldn't be that high in the first place. But if insulin's high and glucose is high, what that's saying physiologically is the pancreas is responding to all this glucose, but it's not getting into the cells because of likely insulin resistance. The receptors just simply aren't working. As one continues to go down this pathway, the next phase would be high glucose and actually normal insulin. Now again, physiologically this also doesn't make sense because glucose should not be high, and if it is, insulin should always be there to help drive it into the cells. If glucose is high, if A1C is anywhere between 5.7, 5.8, what you're looking at then is high levels of blood sugar or blood glucose, normal levels of insulin, and that indicates that the pancreas, for whatever reason, is not able to produce insulin anymore, likely due to some kind of damage. There's a concept that's called lipotoxicity of the beta cells, and the thought is that the beta cells just get so gummed up with these free fatty acids that they can no longer really produce insulin in an adequate fashion. Continuing down that pathway eventually, and this is really seen mostly in late-stage diabetics, is low insulin levels but really high levels of glucose, and that's just an indication that this process, this pathway has been going on for a long time, that they can't make insulin at all anymore, and that the glucose levels therefore cannot get into the cells. So that's how to really evaluate insulin. To do a good job, you need to look at insulin as well as glucose, A1C, to really see what it is that you're looking at. And hopefully that helps with insulin. Let's talk a little bit now about insulin-like growth factor 1. Now, as the name would suggest, it is kind of similar to, molecularly similar to insulin. The process is basically this. You've probably heard of the hormone called growth hormone. Growth hormone is produced from the anterior pituitary. The growth hormone then stimulates the liver to produce the liver's hormone, which is insulin-like growth factor 1. This isn't the only place that insulin-like growth factor 1, or IGF-1, has been found to be produced. It turns out that IGF-1 can be produced locally by cells themselves. And it's a process that's called either autocrine or paracrine. And that essentially means that if I am a cell and I produce a hormone that acts on me, that's an autocrine reaction. Let's say I'm a cell and there's a cell next to me, I produce a hormone, we're in the same tissue together, produce a hormone, and that acts on the next cell within the same tissue, that's called paracrine. If something produces a hormone that goes systemically, that's called endocrine. So, the IGF levels, however, found on a blood chemistry like this panel will likely be liver-derived. Even though cells have been found to be able to synthesize it themselves, that's not likely going to change the systemic blood levels of them, and what you're likely looking at then is IGF-1. So what does IGF-1 do? IGF-1 is considered to be an anabolic hormone. That there's a pathway, and it's an intracellular pathway called the AKT pathway. And this pathway is pretty amazing. This AKT pathway within a cell, when stimulated, has been shown to increase cell proliferation, increase cell growth, increase cell survival, decrease what's called cellular apoptosis, which is essentially the cell breaking down and dying. So it decreases the cell's ability to die. It increases glucose uptake and regulation. Stimulating the AKT pathway within any given cell has been shown to be neuroprotective, for example. So really, this AKT pathway is it's phenomenal in terms of the many, many different things intracellularly that it does. IGF-1 stimulates the AKT pathway within cells. So insulin-like growth factor 1, if low, what one might see is things like cell death or cell destruction or improper cellular function or improper glucose handling, for example, or neurodegeneration instead of neuroprotection. So all these things is why IGF, specifically growth hormone and IGF-1, is considered to be sort of a youthful hormone that does tend to decline with age. So if it's low, if it's high, which is fairly unlikely unless there's actually a sort of a pathological process going on, is what you would see is excess growth, excess cell proliferation, which again, you probably won't see too much of today. The question is do we want high or low levels of IGF-1? And this is true of everything. Insulin has been vilified, cortisol has been vilified, but without them, the body doesn't work correctly. We don't want too much or too little of any of these hormones. What we want is balance. So in terms of what can cause low IGF-1, first and foremost, if you look from where it's produced, it's the liver. If the liver is dysfunctional, then IGF-1 production may also be dysfunctional. It's one of the 300 plus things that the liver does. So if the liver is not doing what it does well, producing IGF-1 may be a particular cause. How can you identify possible low IGF-1 as a liver dysfunction? Looking at other elements on a blood chemistry. So things like low albumin, things like elevations in AST or ALT, for example. Those could all indicate that there's some issue going on with the liver. Also low BUN, for example, since the urea cycle is what takes place in the liver. If you see low BUN, low albumin, perhaps high AST and or specifically ALT, what you may be looking at is low IGF-1 production because the liver is not working as well as it should. Now, assuming the liver is working well, the next really big question is since growth hormone stimulates the liver to make IGF-1, what can cause an imbalance in growth hormone? Because low growth hormone will absolutely lead to low IGF-1 because it's the presence of growth hormone that the liver synthesizes IGF-1. So things that can cause a suppression or lowering of growth hormone are things like increased insulin, hyperglycemia, for example. Those have been shown to decrease growth hormone. Improper sleep, poor sleep, either quality or quantity, have been shown to lower growth hormone. Recently, this class of compounds called xenobiotics have been shown to decrease both growth hormone and IGF-1. Xenobiotics are compounds that might be phytoestrogens, for example. Certain endocrine disrupting pesticides or chemicals have actually been shown to decrease both growth hormone as well as IGF-1. Interestingly, stress can lower these as well, but it's chronic stress. If you look at the literature suggests that an acute stress will actually increase the production of these hormones, but chronically will actually then tend to sort of suppress them over time. Also, along the lines of excess hyperglycemia, excess insulin, other things that you would see associated with that are an increase in free fatty acids, increase in just body fat in general, as well as low lean body mass. So somebody with a high BMI, for example. All of those things, free fatty acids increase, high fat mass, low lean body mass, have all been shown to decrease growth hormone and therefore IGF-1. So if you see low IGF-1, you want to take a good look at the individual. Are they overweight? Do they have low lean body mass? Are they exercising or not? How's the sleep? For example, always consider the exposure of xenobiotics, as well as looking at the other markers on their panel as to if the liver's working well or they might have hyperglycemic tendencies. The last thing that we're going to talk about is cortisol. Now, cortisol is produced from the adrenal glands. The adrenal glands have two very different histological or tissue-based regions of it. The outer portion of the adrenal glands is referred to as the cortex, and that's what we'll be talking about. The inner is called the medulla. Just to be complete, the adrenal medulla makes what's called adrenaline, better known perhaps as catecholamines, and more specifically known as epinephrine and norepinephrine. So those all come from the adrenal medulla. The outer portion of the adrenal glands is called the adrenal cortex. Now, the adrenal cortex has three very distinct histologically different layers. The outermost layer, just to be clear, produces aldosterone. Aldosterone is called a mineral corticoid and helps to regulate sodium and potassium balance in the body, therefore regulating things like blood pressure, osmolarity of the blood, as well as blood volume. The next layer of the three in the adrenal cortex produces cortisol. Cortisol is known as a glucocorticoid, and glucocorticoid, as its name would imply, its primary job is to help maintain stable levels of glucose depending on the need in the body. And we'll talk more about that in just a second. Now, we're not talking about it much here, but the third and innermost layer of the adrenal cortex makes androgens. So things like DHEA and androstenedione, little bits of progesterone, testosterone, and estradiol can all come from the innermost layer of the adrenal cortex. But what we're really talking about now is cortisol, since this is what's on the panel. Now, cortisol is produced via the anterior pituitary, producing a hormone called adrenocorticotropic hormone. In the presence of this adrenocorticotropic hormone, or ACTH, when present, will stimulate the adrenal glands to make cortisol. Now, one thing that needs to be discussed briefly is there's a good chance that somebody getting this panel will do so first thing in the morning after a fast. It needs to be stated, however, that cortisol has what's called a circadian rhythm. That cortisol is highest first thing in the morning and is lowest at night when you're going to bed. So chances are that somebody will be doing a fasting morning cortisol when they do this test, and therefore you would expect cortisol not to show up as high on the blood chemistry because the range will adjust for that. But what you would really see is a relatively high level of cortisol if comparing it to different times during the day. So, under the influence of ACTH, the adrenal cortex makes cortisol. And again, cortisol is a glucocorticoid. Now, really, cortisol can either be too high or too low. If cortisol is too high, some of the things that you may see along with this is, it's a catabolic hormone. And here's the reason why. Cortisol's job, when cortisol is around, it's considered to be a stress hormone. When under a stressful situation, you actually want as much glucose as you can to help fuel the cells and muscles, for example, in a fight or flight situation so that you can flee or fight and ultimately survive. You want high levels of glucose. You want high blood pressure during those periods of time. The problem is over time, now we have chronic stress and possibly chronically elevated cortisol levels. One of the things that you can absolutely see when cortisol levels are high, because cortisol will increase glucose, is actually see high insulin as well, or let's just say blood sugar dysregulation. In somebody with high cortisol, they may have a high fasting glucose, they may have an elevated hemoglobin A1C, and they could be following the best diet, the best exercise program and lifestyle in the world, but internally are making more cortisol, which in turn makes more glucose, which in turn makes more insulin, causing insulin resistance. Unfortunately, people don't know this may be going on in their body, despite following a really good program. These individuals will often tell you, I'm following a great diet and exercise program, but I can't lose weight. Well, if you have high cortisol and you have high glucose and you have high insulin, you will have a hard time losing weight for a variety of reasons. Another thing that you'll see with high cortisol is poor repair. And you have poor repair, again, just think glucose. There are many different pathways to glucose in the body. One of them that cortisol stimulates is the breakdown of proteins. A protein is really just a sequence of amino acids. Some amino acids are called glucogenic amino acids, meaning that those amino acids can be converted essentially into glucose in the cells of our body, specifically in the liver, and that process is called gluconeogenesis. You're making new glucose from something that wasn't glucose before. In the presence of a stress, which is really what this hormone is, your body doesn't care if your skeletal muscles are breaking down because they're providing you fuel the amino acids to be carried to the liver to make new glucose to help maintain glucose levels as being stimulated by cortisol. So it doesn't care how you look in the mirror to yourself. All it cares about is getting the glucose that it needs, and one way is breaking down proteins. So somebody that's had chronically elevated glucose or cortisol for a while may have poor healing, poor repair. They may feel sore after exercise many days because they're not repairing themselves. And you actually might start to see a breakdown of certain things like collagen, which is essentially a protein. So this is a very catabolic hormone. It breaks down fatty acids and proteins and amino acids really to make more glucose. Another thing that you might see in somebody that's had really chronically elevated cortisol is actually poor memory. And it's not just poor long-term memory, it's poor short-term memory. The reason why is cortisol has been found to negatively impact a part of the brain called the hippocampus. And the hippocampus is involved in converting short-term to long-term memory. So if somebody who's been under stress for a long time has high levels of cortisol, you know they have blood sugar dysregulation, you know that they're in a catabolic process, breaking down many proteins in their body, but they also may be breaking down a critical part of their brain that converts short-term to long-term memory, and maybe something that you ask, how's your memory been in the past few years? Have you feel like it's been declining? If they say yes, I can't even remember phone numbers anymore, or I forget to pick up my dry cleaning, or whatever it may be because of chronically elevated levels of cortisol. Now, on the other hand, cortisol can be low. Now, this is a concept in alternative medicine today, falsely called adrenal fatigue, and while that's not entirely true, low cortisol definitely exists, and it definitely causes problems in individuals. People with low cortisol will first of all have a higher sensation of pain in their body. And the reason why is cortisol actually suppresses something called substance P. So if cortisol is low, substance P will be higher, and substance P actually stimulates certain parts of your nervous system that you experience more pain than you would if cortisol was actually normal and substance P was low. So people that will say things like fibromyalgia or chronic fatigue, what you may be looking at is in fact low cortisol. Low cortisol is also associated with muscle weakness and just overall fatigue. And the reason why is if cortisol helps to maintain stable levels of glucose, if cortisol is low, then glucose may go low. You may see hypoglycemic symptoms, and it's very common in people with low cortisol. But then the muscles actually don't utilize glucose and glycogen appropriately and then can feel fatigued. Another classic thing you'll see in people with low cortisol is poor sleep. And it's not getting to sleep, but it's staying to sleep. As glucose goes down while we sleep, cortisol goes up, because if it starts low at night and begins high in the morning, it's going to have to pick up while you're sleeping. That increase in glucose or cortisol while you're sleeping helps to maintain stable glucose levels while you're sleeping. If cortisol is low, glucose starts to drop. It becomes an emergency for the brain, and very often individuals with low cortisol will have hypoglycemic tendencies and symptoms, as well as they will very often wake up pretty much every night. Sometimes around 2 or 3 in the morning as glucose starts to drop. Cortisol is not around to help pick up glucose, and so that's something that they will very commonly see as well. Also, people with low cortisol will have low blood pressure. They will tend to, if they are laying down or sitting, when they stand up, have symptoms or feelings of dizziness. And another classic one that's very important is dehydration. Cortisol doesn't really do much towards dehydration, but the other hormone I mentioned, aldosterone, does. That if cortisol levels are low, there's a good chance that aldosterone levels are also low. Aldosterone, the short version is, will tell your kidneys to reabsorb sodium instead of excreting them as urine. So if you retain sodium, you'll retain water. But if cortisol is low and aldosterone is low, you will tend to eliminate sodium, and with it will go water. And these are individuals that may be drinking adequate amounts of water, very fitness-oriented, health-oriented people, drinking 2 to 3 liters of water a day, but cellularly, physiologically are dehydrated because they're not retaining sodium, and with sodium will follow water. And on a blood chemistry, you may actually see low or low normal sodium and high or high normal potassium concurrently, along with low cortisol, and that's exactly what you're seeing. So I hope you found this particular video on IGF-1, insulin, and cortisol helpful, and I will see you in another video.